So I guess we're live. This is me, this is David Wong, and I came here to tell you a story. So my story starts with a timeline. Two hash functions, SNEFU and MD4, were released in the beginning of the 90s. They got quite popular. Unfortunately, SNEFU quickly got broken by the newly introduced differential cryptanalysis. MD4 remained unbroken for some years and became the de facto standard for a hash function, but also to construct hash functions. So MD here stands for Merkle-Damgard. So the construction became the standard to build other hash functions. And other hash functions using that standard are MD5, SHA-1, even SHA-2, and a bunch of others. MD4, unfortunately, we realized that it's broken, it's not very secure. MD5, we quickly realized that, or not that quickly, and actually MD5, it took a lot of time to deprecate it. It was rather painful, was used all over the place, right? From certificates to storing passwords. SHA-1 got broken earlier this year, right? If you were at Black Hat US, you must have seen Eli from Google giving a talk about that. So no more SHA-1. And now we're left with SHA-2. SHA-2 is really the standard that everybody uses wherever you are on the spectrum of security. If you're a developer, if you're a pen tester, whatever you are, you must have seen SHA-2 or you must have used SHA-2, right? It's all over the place. So the question we had back then was, is SHA-2 going to follow the same fates, right? It's built on the same construction, the Merkle-Damgard construction, that I'm not going to explain here. And if it follows the same fates, do we have a backup plan? Do we have another hash function that you can use to replace SHA-2? And the answer was not that clear back then. So the NIST, an American organization, decided to organize an open competition, like the AES competition, for the new standard hash algorithm, SHA-3. So it started in 2007, lasted for 5 years. 5 years in which 64 different candidates from all over the world fought to become the next standard. So SHA-2 was designed by the NSA. SHA-3 is really an open standard. So 2012, 5 years later, finally KMAC is nominated as the winner. So whenever I say SHA-3, I also mean KMAC. It's the same algorithm. Now, other candidates that didn't make the cut in the last round were Blake, Rostel, JH, and Skyn. It's not that they were insecure, it's rather that we only had one position for the winner. And if you look at Blake, you might recognize that name because it had had a second life after the competition by releasing a second version, Blake 2, and it's been adopted by quite a lot of standards and applications. All right, so 2012, KMAC wins. 2015, 3 years after the end of the competition, we finally have a standard. So it's a NIST standard called FIPS Pub 202. It's kind of an ugly name, ugly PDF. But anyway, whatever, we have a standard. Only 2 years ago, right? So it's pretty recent. So that's SHA-3. And that was my intro to why we build SHA-3 and why and what's SHA-3. And here's my outline. And I'll basically spend a few slides next to explain to you how SHA-3 works. So I'm not going to go too much into the details. I'm just going to give you some intuition of how it works. So don't worry, no equations, no math. It's pretty cool. If you focus on the next few slides, you'll go away from this talk with the knowledge of how SHA-3 works. After that, I'll be looking at Strobe, which is something built on top of SHA-3. It's not a hash function. It's actually a protocol framework. So it allows you to build much more than just hash functions. The third part of this talk will be about Noise, which is another protocol framework. Actually, anyone here has heard of Noise before? The Noise protocol framework? Okay, 2, 3, 4 people, 5. So it's something to build something like TLS. You can think of it like that. And it really doesn't use SHA-3, so there will be a break from SHA-3. And finally, at the end, I'll have a surprise, but more about that later. All right, so time to focus. SHA-3. SHA-3 is something, it's in the field of permutation-based cryptography. In crypto, you have a lot of different fields. One of them is just a field of things built on top of permutations, so that's how it's called. What is a permutation? Well, don't worry, I have a good explanation for that. Everybody knows AES, right? AES, the core algorithm to encrypt things. It takes 128-bit input, plaintext, and it gives you 128-bit ciphertext, right? That's how you can encrypt. And from a ciphertext, you can decrypt and get back your plaintext. So it's a one-to-one mapping between all the possible inputs of 128 bits and all the possible outputs of 128 bits. Right? If you don't have this one-to-one mapping, if you have a ciphertext, you don't know how to decrypt it. You don't know what plaintext you can get. And here I pretend that I use a key of all zeros. So the key is known. Everybody can use it to decrypt, encrypt, we don't care. There is no secret here. So every time you'll see this function here, this permutation, you can think of AES with a known key. I'm going to build something called a sponge construction. This was invented as part of the SHA-3 competition to build the new hash function SHA-3. So this replaces this Merkle dam guard construction that I talked about previously, remember? Okay, what is this sponge construction? Well, first I set the input of my permutation to all zeros, okay? Bunch of zeros. So the permutation kind of randomizes this and I get an output. Now I decide to split my inputs and my outputs in two different parts. The first part, I say the first R bits, and here I choose a very simple example. I have 5 bits here of the input and the output are the public parts. Okay, it's public. And the remaining bits of the input and the output are C bits here, 3 bits, are the secret part. And you're going to understand why I call that public, why I call that secret, but just so that we're on the same page, if it's AES, right, you take the plaintext and you just say the first R bits are the public part, and then the remaining part is the secret part. All right. So a hash function is not very good if you don't take an input, right? So we want to hash something, and here to take the input inside our algorithm, what I do is that I just XOR my input with the public part. And at the beginning, the public part is only zeros, right? Very easy. So here, it's very easy if I have an input of only 5 bits, because my public part is 5 bits, but what if it's larger? Well, if it's larger, it's easy as well. We just split it into blocks of 5 bits, and we XOR the first block of 5 bits with my public part. Okay, we don't touch the secret part. Then we take the second block, and we XOR that with the public part after permuting, after using something like AES, right? We permute again. And finally, if we have only 3 blocks, we XOR the final block with the public parts, and we permute again. Make sense? It's just what we call absorbing, right? It's a sponge function. We absorb a message. Makes sense. Now, how do we get an output? It's not very useful if we don't get an output from that, right? It's a hash function. What we can do is that we can just read the public part. So here we get 5 bits. If we need more, we can just permute and read again. We get 10 bits. If we need more, we continue to do the same. This is called squeezing. All right, it makes sense, right? It's a sponge. We absorb our message and then we squeeze it to get an output. And that's really all there is to SHA-3. So we have a paper proof, a mathematical proof that this works, this is secure, as long as the permutation at its core is secure. How do we know that the permutation at the core is secure? Well, we don't really have a good way of doing that. The best way we know of is just to try to break it. So that's why the competition lasted for 5 years. It's just people trying to break it using linear cryptanalysis, differential cryptanalysis, a bunch of other cryptanalysis, trying to invent new attacks just to try to break it. After quite some time, we get more confidence in the function, and we say it's secure, or we know how to play with the parameters. All right, so that's SHA-3. And now that I got that out of the way, I'm going to explain Strobe. All right, so I'm going to use this sponge thing to build more than that. So going back to that slide, so remember I absorb my input and then I squeeze it to create an output. But what if I don't stop here and I just continue and then I start absorbing again and then I squeeze again and then I absorb again and then I squeeze again? Is that possible? Well, the KMAC team said yes, it's possible, and they came up with a new construction called a duplex construction. And basically that's what happens here. You absorb your input, you squeeze, you absorb, you squeeze, you absorb, you squeeze. All right, that's interesting. What can we do with that? Can we do anything useful with this? Well, one thing we can do that is interesting is that we can absorb a key, right? We XOR a key with our public part. And when we absorb a key, it's very different from hashing. Usually you hash public stuff, and here we hash a key, right? We absorb a key, so it's a keyed mode. When we use a key, keeping the secret part private is very important. If you leak the secret part somehow, I don't know, some memory disclosure, then the attacker might have the entire state, right? The public part and the secret part. And now the attacker can reverse all the permutations there is. There is only one here, but if there was multiple permutation, he could reverse all the permutation to go back to the key. Remember, I said a permutation is basically like AES with a non-key. That means if you have the ciphertext or the output, you can get the plaintext or the input, right? So you can reverse this thing. So really, when you're using a key, when you're in keyed mode, you really want to keep that secret part secret. Anyway, we absorb a key, we permute, so we get something kind of random. You get the idea? How can we encrypt from that? Right? We absorb a key, we permute, we get maybe here 5 bits, 5 random bits. How can we encrypt something like that? Well, very simply, if you think of one-time pads or stream ciphers or things like that, you just XOR your plaintext, what you want to encrypt, with this bit string, this random bit string, and you get your ciphertext. And to decrypt, you do the inverse. You generate the same thing via the absorption of the key, and you XOR that with the ciphertext, and you get back the plaintext. Right? It's encryption 101. Okay, but if you know about encryption, probably you know that we never just encrypt and send the ciphertext like that. Just because if there is an attacker in the middle, the attacker in the middle can tamper with the ciphertext. And when we receive the ciphertext, after decryption, the plaintext will be tampered with. So usually we want to protect the integrity of the ciphertext by generating something out of that ciphertext that we can append to the ciphertext. And like that, we can make sure that nobody modified it, right? Usually you use something like AES GCM that takes care of that. So here, very simple way, we can just absorb the plaintext, permute, exactly like we did for hashing, right? And we create basically a hash out of that plaintext and out of the key, because we absorbed everything. So the thing here in the public part will be generated via everything that was absorbed. Okay, so on the other side, when we receive the ciphertext and the tag, we decrypt the ciphertext by doing this little dance. Then we absorb the plaintext that we decrypted, and if it generates something different, then we know that someone modified the message. All right, these are details, you don't have to understand everything here, but this is what we can use this duplex construction for. What if we want to encrypt again? Well, we can just continue here and permute again, do this little dance to encrypt, and then do this little dance to generate an authentication tag to authenticate the ciphertext. And it works. We didn't set up any nonces, any counters, any IVs. It just works. The second cool thing here is that when I generate this tag number 2, I don't only authenticate this ciphertext here, but I also authenticate this one here that I absorbed and the key. So basically, whenever I authenticate something, I authenticate the whole session, not just the last ciphertext, the whole session. So this is a very cool property to have for a protocol, because like that you can make sure that you have consistency on both sides of the connection. Nobody has reordered messages, replayed messages, inserted things, or dropped things. Both sides of the connections are seeing the same thing. Strobe, so the point of my second part, is a protocol framework that gives you access to the duplex construction. So you have all these functions here, and you have what they do on the duplex construction. So don't look too much at that. It's just a nice diagram. But basically that's what Strobe is. It really gives you access to these states, and every time you do some operation, you continuously mutate that state, influencing new things that you're going to do in the future and being influenced by what happened previously. So before I get too much into the details, I just want to give you an overview of how you would use that as a developer. So a very simple example, okay? What does it mean to use this Strobe protocol framework? So we're going to build a protocol, and I have 2 devices. I want to encrypt communications between them. What I will do is that I instantiate a Strobe object via this function and a string. So for example, mywebsite.com or my protocol or something like that. Then I absorb a shared secret. So I absorb it with a function called AD that Strobe gives us, authenticated data. And I do that on both sides, right? So shared secret. So both devices have this shared secret. And now I have a secret in place, so I can encrypt. So I can use the send encrypt command to encrypt a GET request, for example. Right? Makes sense. I'm sending some encrypted data. Of course, I want to authenticate what I just sent, so I use the send MAC for message authentication code with a 16-byte MAC, and I send that. And on the other side, I receive it, so I do the inverse operation to decrypt. I use receive enc, and I use receive MAC to verify the tag. If it's incorrect, it means that somebody must have tampered with the connection, so I can just abort the connection. A very simple protocol, right? I just use these functions on both sides of the connection and I encrypt my data. Now, if I want to continue encrypting, I would just continue to use this send enc and send MAC to encrypt and authenticate. And I will never have to figure out how to create some nonces or some IVs. And every time I authenticate the whole session, not just the last thing I sent. So Strobe is first and foremost this thing. It's a flexible framework to build some protocols. It's more than that though. Since you have access to all these commands, all these functions, you can kind of mix and match them to create just simple cryptographic operations. What do I mean by that? Well, imagine you want to hash. You have the code of Strobe because you're using it to, I don't know, build your protocol. So you can just use Strobe to instantiate it as a hash function. And here I call my hash function David Wong hash. It's my hash. I absorb the message I want to hash with the same AD function, and then I use another function PRF to get an output. And here I want a 32-byte hash. So here I just use the same code base, to just use it as a hash function. So it's very interesting because you get not only this protocol framework, but you also get a cryptographic library for free. All of that relies on the SHA-3 standard. It uses the permutation inside of SHA-3. So the security comes from somewhere. It's not just roll your own crypto. And since it only relies on SHA-3, it's very, very, very small. It's only 1,000 lines of code for the reference implementation in C. There is a Python implementation. There is, I made a Golang implementation. It's also 1,000 lines of code. So it's very small. It's very good for embedded devices and all that stuff. So if you want to look at the specification, it's on strobe.sourceforge.io. It's created by Mike Hamburg, and it's alpha. So it's still experimental, but it's built on solid foundations. All right. So that's basically what is Strobe. It's just this kind of protocol framework built on top of SHA-3. So now I'm going to talk about noise. So if you kind of lost track of what I'm talking about, I'm really taking a break from SHA-3 so you can get back into the talk now. What is noise? Noise is a protocol framework to build stuff like TLS. So I'm going to be talking about TLS first, just a recap. So what is TLS? TLS is the de facto standard for encrypting communications, right? We have other standards like SSH or IPsec, etc. But TLS is really the most popular one, right? It's a very complex specification. I don't know if you've tried to read the specification of TLS. It's called request for RFC, request for what? Request for comments, thank you. RFC request for comments, it's a lot of them actually. You have SSL version, I don't know what, TLS 1.0, TLS 1.1, TLS 1.2. So depending on what you want to support, you have to read several ones. And also a bunch of these have been broken in the past. So there is that. It's not just one specification. It's also, if you start reading one of them, you have to read a bunch of them. So there are a bunch of them for certificates, if you want to use certificates and a public key infrastructure. There are a bunch of them if you want to use different cryptographic primitives. There are a bunch of them depending on the extensions you want to use. Of course, certificates have their own extensions. And it's a lot to digest. If it carries a lot of legacy decisions, a lot of things are done to really support older versions. So if you look at TLS 1.3, you will see that a lot of messages really look like older versions of TLS or SSL, just because otherwise nobody knows how to parse these messages and it breaks the internet. So it's kind of ugly and because of legacy. And of course, if you want to use it, you have these huge and scary libraries. I'll just mention OpenSSL, but basically OpenSSL is so scary that people have forked it to make it better. So you have like boring SSL or LibreSSL, etc. If you want to use it, it's not that simple. So you have to configure it, and the documentation is not very clear usually. So you have to read these books, but then these books are pretty old, so it doesn't really work for the new versions. And so I'm a security consultant, and I often look at clients using OpenSSL, and most of the time they forget to use the right function to, I don't know, verify certificates or verify the host name in a certificate, or just verify the return value of a function, and then you have an open fail. So it's quite tricky to use. Now, if you want to implement it yourself, first, don't even try to do that. It's impossible, right? So that's something I tend to look at also as part of my work, and it's always riddled with bugs. So that makes my job more fun. But don't try to do it yourself. If all these libraries have had their share of problems, right? You have a lot of vulnerabilities found every day, not every day, but you have a lot of problems. It's not because there are bad developers. It's really because TLS is very complex. It's complex to implement. So that's bad. And worse, the kind of thing I see sometimes are reinvented protocols, proprietary protocols that are influenced by TLS. So usually that's completely broken. So don't even try. So here the problem is that complexity is the enemy of security. TLS is way too complex to use or implement. It's hard. It's not easy. People make mistakes, but it's not their fault. This thing is not easy to use. So do we have an alternative? If we want to use something else than TLS, what is out there? Well, the noise protocol framework is exactly that. It was invented by Trevor Perrin, the inventor of Signal, the Signal protocols. And it's a framework, so it's exactly like the Strobe protocol framework. It's not something you can use out of the box. It's something that you can use to build a protocol, something that you can use to build something like TLS. So, for example, in TLS, most of the time you will use certificates or a public key infrastructure. And if you don't want to use these, it's tricky. It's very tricky. In noise, you can just use plain keys. You don't have to use these certificates. And if you don't want to use a public key infrastructure, if you already know the public key in advance, for example, if you have some shared secret or something like that, you can do that as well. It's very easy to do that. So noise is actually a lot of different handshakes, a lot of different ways to do things that you can choose from. It's very flexible. So if you look at the specification, you will see that maybe not half of it, but a large part of the specification spends a lot of time analyzing all these handshakes and telling you what kind of security you get for what kind of handshake you're choosing. Once you know what you want to use for your specific setup, it's very straightforward to implement. It's around 2,000 lines of code if you want to implement the whole of noise. And usually you just want to implement one part. You don't have to implement it yourself, of course. You already have libraries in all major languages to use it. So you just use these libraries and you build your own protocol out of that. And once you have what you want, there is a minimal configuration or zero configuration, and it just works. It's not just a weird protocol that I'm telling you about today. It's used by WhatsApp, it's used by Slack, by the Beacon Lightning Network. It's used, I've heard, by governments, but I don't have any insight into that. It's used by a lot of people, so it's not just a weird spec. So bottom line, if you have a good excuse not to use TLS, noise is the answer, not anything else. All right, so I'm going to spend a few slides trying to explain to you how noise works. So when you use noise, first you have to choose what cryptographic functions you want to use. There are not so many, and you don't negotiate which one you want. You just have to choose in the beginning, and then you have to use these ones you cannot change. So for the key exchange, you can use Curve 25519 or Curve 448. They're pretty famous. Actually, Curve 448 was invented by by Mike Hamburg, the creator of the Strobe protocol framework. Anyway, if you want to encrypt, you can use ChaCha20, Poly 1305, or AES GCM. One is fast in software, the other one is fast if you have hardware support. And finally, if you want to use a hash, you can use Blake2 or SHA-2. So remember, this Blake, it was in the SHA-3 competition. And you can also realize that there is no SHA-3 in there. We're really far away from SHA-3. All right. So you have a client, you have a server, you want to encrypt data. So first you do a handshake. If you know TLS, it should be pretty straightforward. If you don't know, then it's going to be protocol 101 for you. So here a client and a server exchange what they call ephemeral keys, keys that are generated only for this session, right? Those are not long-term static keys. Once they exchange these keys, they can do a key exchange. They can do what we call defilement key exchange, and then they get some shared secrets that they can use to encrypt in what we call a post-handshake phase. So here's just application data, whatever you want to encrypt. So really protocol 101 here. This most simple kind of key exchange you can do. Noise call ephemeral keys E, a token E. And when you do a defilement key exchange with two ephemeral keys, you will call that EE. That's how noise works. And then noise writes this kind of handshake by just writing it with this syntax, where you send a client's ephemeral key, and then the server sends his ephemeral key, and then they do a defilement key exchange on both of these keys. So that's the notation you will see if you look at the specification. There are other tokens. There is a token for static keys, long-term keys. And since there's another kind of key, you can do different kind of defilement key exchange, where you mix an ephemeral key of the client and the one of the server, or the inverse, or you do a defilement key exchange with both static key. And if you have already a pre-shared key, a pre-shared secret, you can do that kind of key exchange as well. So really a lot of tokens, and these tokens are used to build a lot of different protocols, a lot of different handshakes. And they have names, and you really have different handshakes for every situation. If you want to authenticate the server via a public key infrastructure, you can. If you already know the public key of the client, you can authenticate the client like that. If you have a pre-shared secret, you can use that. A lot. This is not an exhaustive list. You have a lot of them. But today, for this talk, I'm just going to focus on the NX handshake. The first N means that the client is not authenticated. The second letter X means that the server sends its static key as part of the handshake. So that might ring a bell. If you know how HTTPS work, that's exactly the web browser, web server scenario, right? When you go on HTTPS, google.com, the browser doesn't send a key, doesn't send a certificate, but google.com really sends you a certificate, right? So that's exactly what's happening here. So I chose this handshake pattern so like that if you know TLS, you know HTTPS, you can understand and can follow more easily. All right, so let's read the first token there. It's an E token. That means that the client has to send an ephemeral public key, has to generate one and to send it. And now the client is done, there is nothing more, so the client can send a payload. It can be anything, it can be, hey, I want to talk to that server, not that server, or it can be the name of the client, it can be anything, but it's not encrypted. Now is the server's turn, right? So the server has to generate his own public key, ephemeral public key, and send it. And I call that RE for remote ephemeral. Now we have two keys, we exchanged two public keys, so we can do a defilement key exchange on both of these ephemeral keys, which output a shared secret, which we can use to encrypt the next token. The next token is a static key, and so here I call it RS for remote static. Encrypted, we can decrypt it, and now we have a new key, the static key of the server, that we can use to do this ES, which is a defilement key exchange between the ephemeral key of the client and the static key of the server. And then it's the end of the handshake pattern, so the server can send a payload as well and encrypt it with the new key derived from that last key exchange. That payload can contain whatever the server wants to send, probably here a signature over its public key from some certificate authority or something like that. So that's about it. That's what noise does when you do an NX handshake, right? You exchange some public keys, some ephemeral public keys, some static public keys, you do different key exchange, and then you can encrypt. Simple as that. All right, so I'm going to be talking about that more. I'm going to go through that key exchange one more time, but this time I'm going to be more specific. I'm going to show you the internals of noise, what's happening under the surface. And this is my most complicated slide, so time to focus again. It's quite heavy. And basically here you only have the view of the client, just because I don't have enough space to put the view of the server as well. On top, you have 3 different states. They don't matter too much. Those are just structures where you can store some values. If you kind of know noise, you can follow along. Otherwise, you can just ignore them. So the first thing you do when you go through a noise handshake is that you initialize both the client and the server. What they're going to do is that they're going to hash this string. And here, this is the name of my protocol. This is noise_NX, my handshake pattern, _25519, my key exchange algorithm, then AES-GCM and SHA-256. I'm pretty conservative. I'm choosing these algorithms. I hash that and I store that into a value called H. More on that later. I also store that into a value called CK for chaining key. Again, I'm not going to explain that yet. So now remember, the client sends an ephemeral public key, right? So first the client has to generate it and store it somewhere. And now we're going to do something weird. We're going to hash that public key that we send with the previous H value, and it's going to give us a new H value. All right? Now it's time for the client to send a payload, whatever the client wants, can be empty. And we're going to do the same thing with the payload. We're going to hash the payload with the previous H value that we just got from that previous thing. And we get a new H value. And this kind of looks like I'm absorbing everything I'm sending, or you will see later, receiving. So you can see this is kind of a hint as to what I'm going to do later. I'll change this part by just by absorbing it. But this is pretty much what the H value is. It's an absorption of every message we send and receive. So it's the same thing on both the client and the server. Now the server, it's his turn, sends a remote ephemeral public key. So we store that somewhere, and we absorb that. Now we can do a diffie-element key exchange, and we put the output into HKDF, which is a key derivation function, with the CK value, this chaining key. It gives us the next chaining key and a key that we can use to encrypt. And so you can see here, the chaining key is really used to generate encryption keys. Now that we have a key, we can decrypt stuff. It's good because the server is sending us an encrypted static key. So we can use the key we just generated to decrypt it. And here, if you know AES-GCM, you know that there is an authenticated data part that we can use to authenticate anything we want. So here we authenticate this H value. And by doing that, we authenticate the whole transcript. We authenticate the whole handshake. We make sure that the server is seeing the same thing we're seeing, the same sequence of messages. So it's a very good property of noise. Of course, we absorb the ciphertext we just received. And now we have a new key, the static key of the server, so we can do a new diffie-element key exchange. We put that into HKDF with the chaining key to derive a new key and a new chaining key. Finally, we receive a final payload. The server is done. We can decrypt it with the new key we created. We can authenticate the H value, so we make sure that the handshake looks the same on both sides. And we absorb this ciphertext. And now the handshake is done. So what we do finally is that we put the last CK, the last chaining key, into HKDF again. It gives us 2 keys, 1 key to encrypt from the client to the server, 1 key to encrypt from the server to the client. So it's like TLS. All right, that's quite tricky, right? It's kind of dense. I don't know if you could follow that. If you're watching the video on YouTube, then that's better because you can rewind, right? But yeah, one of the points of that slide is really that it's complicated. It's way less complicated than TLS, fortunately, but it's still kind of dense. So what I'm going to do is that I'm going to simplify that. And that's really the last part of my talk, which is called disco, which is a merge of noise and strobe. That makes sense, again, noise, strobe, disco. And I'm just going to simplify, because when I looked at noise, I was like, I can simplify that using strobe. I can make it more elegant, more smaller, easier to implement, and all this stuff. And I'm going to show you how I did it. So going through the same handshake one more time, the 3rd time now, but this time using Strobe. So I initialize it, and this time I throw out AES-GCM and SHA-256. I actually throw out also HKDF and HMAC that are used in noise. I throw out a lot of this symmetric cryptographic algorithm, and I just replace it with Strobe. So your code base is now much smaller, much simpler. And I use this init Strobe function that Strobe gives me to instantiate Strobe objects. Now remember, I have to send a public key as the client. I have to generate that public key first. Nothing changed. And now I can absorb that public key in my state with this send clear function. It makes sense, right? We're sending something clear. We're sending a payload now. Well, I can just use this send clear function to send my payload and absorb it in my state. All right, the server's turn. We receive a public key that we store using the receive clear function, right? We receive it in clear. Makes sense. Now we have two ephemeral public keys. We can do a key exchange, defilement between these two keys, and we absorb the result with this AD function that Strobe gives us. Now we receive an encrypted static key. We can just decrypt it and also authenticate the whole handshake, everything that we've absorbed so far, via this receive AAD function, which is really receive encryption and receive MAC. Now we can do a new defilement with that static key that we just received, and we absorb it with this AD function. And now we receive a payload that we can decrypt with this receive AEAD function. And that's about it. That's the same handshake that I went through previously, simplified by Strobe. Here, if you had to implement that, it looks easier, right, compared to the previous diagram. And much more simple. And here at the end, if I want to separate, I have two states, one for the client to encrypt and one for the server to encrypt. I can just clone my states and kind of differentiate them into two different states, and I can use one for the client, one for the server. And here I can just continue to encrypt and continue to decrypt. I don't set up nonces or IVs or counters, and every time I authenticate something, I authenticate everything starting from the handshake. I want to go through the same handshake one last time, but to show you exactly what's happening with that duplex construction. And this is something I really couldn't have done with AES-GCM and SHA-256 and HKDF and HMAC, but I can do it because it's so simple and so elegant that I can actually show you what's happening under the surface. So here, when I initialize, what I'm doing is that I absorb this string by XORing it with my public part. So remember in the diagram that I had on SHA-3, I had the public part on top. Here, I just rotate it, and my public part is on the right, my secret part is on the left. So to absorb this string, I just XOR it with the public part. Now I need to send a public key, I generate it, and I just XOR it in my public part. If I reach the end of the public part, I can just permute and start again on a new block, right? Exactly what I was doing when I was hashing with SHA-3. I send a payload, what do? I XOR it in the public part. Now I receive a public key. I'm just going to absorb it also. I'm just going to XOR it in the public part. It's pretty easy, right? It's pretty elegant. Now I'm doing a defilement between the two keys. I just XOR it in the public part. Now I receive the encryption of the static key and a tag. I do this little dance where I permute and I generate some random bits out of everything that I have absorbed, including the key exchange, and I can decrypt the payload. And then I can permute again to generate some tag, verify that it's the same one that I received. Otherwise, somebody's man-in-the-middling me, and I can cancel the handshake. Now I can do a new defilement with the new static key that I absorb in my public parts by XORing it. And finally, I receive a payload encrypted, so I can do this little dance again to decrypt it and to generate a tag that I can verify. And that's it. The handshake that Noise is doing, or rather now we can call it Disco, is this thing. And it's pretty simple, right? We're just XORing stuff, and sometimes we're permuting. Compared to the previous diagram, it's pretty elegant. So Disco is on discocrypto.com, pretty easy to remember. And what is it? It's a draft specification. It's an extension of Noise, that Noise protocol framework, right? Still a draft, still experimental. From that, I made a library called libdisco. So it's a plug-and-play protocol. So it allows you to do something like noise, where you can encrypt communications between two devices or more. But since I'm using Strobe, it's also a cryptographic library to derive keys, to hash, and so on. So it's a protocol and a library. It's written in Golang. It's available at the same address, so the specification and the library at discocrypto.com, so you can go on it today. And the whole lot is only 1,000 lines of code if you don't count the primitives, the cryptographic primitives. So if you want to audit libdisco, it's very, very short. It's very small. Of course, it's not very useful if you don't have the cryptographic primitives. So if you want Strobe is very small, right? It's only 1,000 lines of code. So the total is 2,000 lines of code. Finally, if you want to use the protocol, you need some key exchange algorithm. Curve25519 is 2,000 lines of code, so you have to add that. So the entirety of the library, with Strobe, the cryptographic library, and the protocol is the same amount of lines of code as Curve25519. So it's extremely small. If you want to look at the code and make sure it's secure yourself, you can do it, right? It's not gonna take you that long. It's based on noise, which is, let's say, a stable draft at this point. It's being used, I mean, WhatsApp use it for, I don't know how many users. Strobe is alpha, but I suspect it's being used by Rambus at the moment, since it's been developed there. Disco and libdisco are completely experimental. So I came here today to give you a glimpse of what we have, what new things we have in the applied crypto world, and what it's going to change the landscape of the applied crypto, but it's going to take some years. Now, I came here also to hype some people. I need more eyes, more testing, and at some point down the line, we might have something that is very small and way less scary than TLS to encrypt our communications. So that's about it. The whole disco stuff, again, discocrypto.com. I write a lot about crypto on my blog, cryptology.net. I write about security, technical articles, or less technical, so come take a look there. And you can follow me on Twitter, Lyon01_David. That used to be my city in France. And of course, I work at NCC Group. So if you need someone to look at your crypto, call me, give me a call. If you're a consultant or if you're in the AppSec team of your company or anything like that, you can also talk to me. I'd be happy to help you or talk to you about crypto or security in general. So yeah, I'll be here or at the conference if you need me. Thanks. Some questions? There's a mic.
Hi. So I didn't see in the protocol the presence of a static private key. How do you verify who you communicate with? So,
like I said, Noise NX is pretty much like the web browser, web server scenario. So, all right, I have to go through that again. But basically, remember I said that you can send a payload at the end of a turn, right? The client sends a payload at the end of its turn. And here, the server can send a payload at the end of his turn.
So that's the point where you can include parameters which verify your communicating partner.
Exactly. In Noise NX, probably you would include a signature from some authority, right? That the client trusts.
I understand. Thank you.
Sure. Another question?
Next question.
Question here.
Yeah, thank you for a nice presentation. I really appreciate that TLS is going to be extinguished, hopefully. But still, yesterday there was a talk that we shouldn't put all our trust in like one cryptographic primitive, because in case it is shown that it becomes broken or backdoored, then we are kind of screwed, right? And here, what you're doing is basically using SHA-free for everything, right? So in case there's a vulnerability or weakness or backdoor in SHA-free, that means that all of this is broken as well?
Right. So there are two different schools of thought, I would say. There are the people who think you shouldn't put all your eggs in one basket and have as many cryptographic primitives that we can have. For example, TrueCrypt, you can choose what you want to use to encrypt. TLS, you can choose your primitive. The other school of thought is that we've had a lot of things broken in the past, and this cryptographic agility is kind of a mess in TLS. So it's better to make sure that one thing works well and just use this thing for everything else. So like that, if you want to audit your system, you have just this, I don't know, 1,000 lines of code. Actually, SHA-3 is even less. It's like maybe 200, 300. If you go on Twitter, there's a Twitter account called TweetFips202. It's 9 tweets. If you concatenate all the tweets together, it's an implementation of SHA-3. It's very, very small. So it's better to have one thing to audit and then make sure it's secure. And like that, everything else relies on that. And you don't have many threads running around. Now, if one day we realize that the permutation of SHA-3 is broken, we can just replace it and it should work because we have proof that the construction on top of it works, right? So does that answer your question? All right. Another question?
All right, we still have 10 minutes, so if you have any question, just ask.
Thanks for the talk, very nice. I had a question, you still rely on asymmetric keys to prove the identity of the party you're communicating with?
So you don't have to. This is one example. This is not NX. You have other handshakes where you can just use a pre-shared key. So no public key. Well, you still do the ephemeral public key part, but you rely on that shared secret. So not on a static key, long-term static key.
I'm asking that because I saw a talk recently talking about quantum computing and how it could affect the trust we have in asymmetric keys. Is there a solution you have in mind for this kind of problem?
Oh, so for quantum crypto, pretty much all the symmetric crypto we have should withstand whatever quantum computers we have one day, if we have any. When it comes to public key cryptography, so here Curve 25519 or Curve 448, probably it would be more difficult. So right now we have a NIST kind of open thing. It's not a competition where a lot of people have submitted designs for signatures, for key exchanges that are secure against quantum computers. I think it was over like 2 days ago or something like that. So research is ongoing. This is not something that we have now, or rather we don't have confidence in these algorithms now. But in the future, maybe in 5 years, 10 years, we'll have solid post-quantum crypto.
Thanks.
Another thing I can tell you about that also, Google Chrome made some experiments. They included a post-quantum key exchange, but since they were not sure it was secure because it hasn't received the same amount of cryptanalysis, they also included a normal key exchange, so something like 25519. And what they would do is that they would do 2 key exchange in parallel, one with an algorithm that we know, that we're fond of, that we think is secure, and one with the post-quantum crypto algorithm, and then they would XOR the results to use that as a key. So like that, if the post-quantum crypto turns out not to be secure, you can use the other one, you can rely on the other one. If one day we have post-quantum computers, you can rely on the post-quantum crypto algorithm. So those are called hybrid schemes where they mix both algorithms together, like that you can rely on both of them. Yeah.
I just allow myself to add for the Google Chrome experiment because I was busy with this. It was the New Hope algorithm,
Right.
and they embedded it into an ECC because a signature was not included. The algorithm itself is secure, and it's used by Infineon now for new contactless chips. They produce these chips already.
Are you talking about the post-quantum algorithm?
Yes,
Okay.
New Hope.
Right.
Yeah, they prepare themselves for connected car infrastructure.
So that was New Hope. But what I
Yes.
understood that they did was to do that hybrid scheme where they would use New Hope as well as
Together, exactly.
Right.
That's what they did. They embedded New Hope in a ECC elliptic curve scheme.
right.
But New Hope has no signature integrated, so that's why they did it.
Right. But it's quite interesting. And I believe that this is not in Chrome anymore. So that was just a test and they removed the test, but they were just testing. All right. Any more questions? I guess we can call it. Yeah. All right. Thank you.